kind of summary of who I am and things like that. I think Bill gave a pretty good introduction there, but so yeah, my name is Adam Zeglin. I am one of the co-founders of Instacluster. If you do have any questions that you'd like to direct to me personally at any time, you can reach me at adam@instacluster.com. And yeah, these days I've had various different roles inside the company. I kind of initially started as being one of the people kind of building our core managed services platform. But these days I relocated to the United States, although I am actually about to move back to my homeland of Australia. But these days my main focus is on Apache Cassandra, the open source community around that, and then also the various open source projects that Instacluster develops and makes available for the various technologies that we support. So the company, Instacluster, we basically do a number of things around these technologies. Primarily, we have a managed service that provides Cassandra, Kafka, Elasticsearch, Redis, and other technologies that we're kind of looking at introducing in the future on the cloud across all the the common providers, AWS, Azure, etc., and also as a on-prem managed solution. For people who aren't really comfortable with kind of giving the reins over to somebody like us to kind of manage their infrastructure, we also provide support for these technologies. So we can be your kind of tier 2 or tier 3 support people, providing assistance for technologies like Cassandra. So you can call us up if you have any problems there. The managed service and that support offering, we currently manage and support nearly 4,000 nodes of Cassandra and these other technologies. We've been around for coming up for 6 years now, so we have a lot of experience with these technologies and kind of a lot of support hours under our belt, so we kind of know how to solve pretty much all the common problems. That support capability is available 24/7 by 365, so there's always somebody available if you need some help. And then apart from that, we also provide consulting services and workshops and things, and we run webinars and so on, such as the session that you're watching today. So enough of the kind of salesy stuff. Let's have a look at the agenda for today's presentation. Essentially, we're going to cover 7 different aspects of Cassandra that will surprise you in production. And we're going to start with Tombstones. They're always a fun one. And then related to that is repairs. Then materialized views is something we see a lot of people use in production, and it causes some big problems there. Secondary indexes as well. And then kind of some more client-side stuff to do with driver settings, kind of poor schema design, and lack of denormalization of data and things like that. And also have a look at unoptimized queries that can sometimes cause problems with performance of Cassandra. So let's get stuck into number 1, which is Tombstones. So in Cassandra, Tombstones they're essentially a necessary evil, and I'll use that phrase for a number of things. Repairs are also a necessary evil. Compactions are also a necessary evil, but the Tombstones is probably the one that people hit very, very often. And essentially, Cassandra uses Tombstones for various things, but essentially it's how you delete data. And what good is a database if you can't delete any data out of it? So because that's how you delete data in Cassandra, you end up with dealing with Tombstones if you do deletes, and then you kind of have to manage those. So essentially, Cassandra has 3 major types of Tombstones. Those are the ones that get created when you issue a delete query. There's also Tombstones that occur when you insert data with a TTL. So essentially, it's an implicit. And then the last is if you insert rows with null values in any of the cells rather than leaving them unset. So that's a very I guess, slightly, what's the right word? Kind of, it's a minor thing, the difference between leaving a cell, in a row in a table unset versus explicitly setting it to null. There is a subtle difference behind that, right? So it's worth watching out for. Also worth noting is that inserts and updates to the various collection data types you can use. So you can have a cell in a table be Cassandra is a distributed database, and in order for every replica of the system to know that you've deleted data, you need to essentially write a indicator to every replica. Otherwise, you can end up in a situation where if replicas are out of sync due to a network partition that's temporary or something like that, you might delete data off, say 2 out of the 3 replicas. And then when Cassandra comes back online, it actually goes, oh, well, hang on, there seems to now be data missing because one of the replicas has the information and the other 2 replicas don't. Maybe we should fix that, right? Whereas Tombstones solves that problem. You write the tombstone to, 2 out of the 3 replicas, and then it looks like the tombstone is the thing that's missing. So you replicate the tombstones to the 3rd replica, and now the data is essentially marked for deletion on all replicas in the system. And a process, so Tombstones mark the data for deletion. The process of actually reclaiming the space on disk is Cassandra's compaction. So it essentially goes along and finds, if the various data files on disk are eligible, it will go through and find rows and the tombstones for those rows and see that they're eligible for compaction. And if that's the case, we'll actually reclaim the disk space for those rows. That only occurs after the GC grace window, which is essentially a period of time that allows all replicas in Cassandra to get in sync with those tombstone writes. Otherwise, you get back into that problem of things get out of sync and data might reappear if you're not careful. So I mentioned compaction here, so it's probably worth just having a quick refresher on compaction strategies because there's various different types of compaction strategies available in Cassandra. And I'll just go through these quickly because they're kind of more for background information. But essentially, you have size tier compaction strategy, which is good for insert heavy workloads and kind of general stuff. And it pretty much just compacts SS tables of a similar size together, and over time you kind of end up with this tiering of a whole bunch of small ones get combined together into a slightly larger one. A bunch of those larger ones get combined together to a even larger table, and so on and so forth. But the problem there is it can result in large SS table files on disk over time, and minor compactions may not end up reclaiming disk space, especially if you do, say, an insert and then a lot of time later do a delete, because you end up in a situation where the original row is in a really large SS table file and the deletion tombstone is in a new smaller SS table, and the chance of the large one and the small one getting compacted together is very, very slim, and it could take a really long time before the compaction will actually have the opportunity to reclaim the space off disk. And the other thing is it also requires a large amount of free space available. We sort of say between 50 to 70% is kind of a good safe space to be in. The next one is level compaction strategy, which is essentially great for low latency read performance. So for read heavy workloads. So if you're doing more reads than writes, level compaction is better. The general concept here is that it compacts various SS tables into levels, and each level has a maximum number of SS table files inside it. So essentially, when you do a read, you are only going to be reading from a single SS table file per level. A visual diagram would probably be a little bit more useful here, and we do have one available. So reach out to us, and I can provide a little bit more insight into the details of you know, the complexities of things like leveled and so on. Essentially, as I said, this is just a refresher on a bunch of these concepts. You know, I encourage everybody to actually go and do their own research on these things, because picking the right compaction strategy is actually quite important. You know, for the correct operation of Cassandra. So you've got level compaction strategy, size decompaction strategy, and then lastly, you also have time window compaction strategy, which is very similar to the older date-tiered compaction strategy in older versions. And time window is, as its name kind of implies, it's all to do with time series data, and I should say that that's immutable time series data, i.e. you insert it once with a TTL and want to have it deleted after, say, 6 or 12 months. You never update or modify that information once it's been inserted. And it's very, very efficient, because it essentially, it's like a conveyor belt. Everything gets put on at the beginning, the conveyor belt slowly moves across, and then after 6 months, the data just drops off the end of the conveyor belt into the trash can. There are some caveats. You know, I say it's immutable. The thing is, if you update data outside of like the initial update window that is defined, then you can kind of have problems where, while certain parts of the data will actually fall off the end of the conveyor belt, the disk space won't be reclaimed until all of the pieces of the data have fallen off the end into the trash can. And so therefore, if you insert data, say today, and then in 5 months you update that data, well, today's information will drop off the trash can in a month, but the remainder won't actually drop off until, you know, another 6 months. So now you kind of end up not being able to reclaim disk space for you know, up to essentially 12 months of time. So don't update things once you've used and also don't mix various types of TTL values together either. So, you know, don't insert rows with you know, a 1-day TTL and then also insert records with a 1-month TTL, because it'll kind of cause problems with trying to reclaim space as well. So problems that we see with Tombstones is essentially the big one is you know, increased disk usage, just because Cassandra's compaction is unable to reclaim the space on disk for whatever reason, i.e. you know, it's not able to, a minor compaction does not consider various SS tables to be candidates for compaction to reclaim the space, or data is not being expired in a ready manner, things like that. So that is where tuning the compaction strategy is important, is to kind of fix the increased disk usage problem, but also making sure that, you know, you're not updating data or deleting data that is too old, because it can actually, you know, be impossible to reclaim the space after a while. There's also an issue when you actually have too many tombstones, i.e. you've done a lot of deletes, that you end up kind of overloaded with tombstones. So essentially, whenever Cassandra does a read, you have to read all the tombstones as well off disk. And so essentially, you're reading a lot more data than you're going to be returning to the client, which can result in higher read latency. You're going to be reading more data off disk. So, you know, it kind of is a performance degradation. And essentially, Cassandra actually has some thresholds where the first is a warning threshold, and then, you know, it'll actually cause query failure after a period of time. It says, you know, how many SS tables, how many tombstones are you able to encounter, or a failure scenario, right? So deleting too much data, not actually having Cassandra reclaim the disk space and get rid of those tombstones, can actually cause query failure down the line as well. So, there's, I mentioned explicit deletes at the beginning, the types of tombstones you can get. So here's a bunch of different type of delete queries that, cause tombstones. There's actually different types. You have partition deletion tombstones, row deletion, range deletion, and cell deletion, just depending on what type of information you delete. And essentially, deletes are writes to disk, right? Cassandra, everything is a write to disk. Essentially, we're writing a little marker that says, this information is going to be deleted. And I mentioned, right back at the beginning that, if you have problematic clusters, i.e. they're a little bit unstable, or if you're not running repairs, which I'll touch on in a minute, you can actually have data be resurrected because the tombstones don't end up being replicated to every node, and then you end up in a situation where the deletion indicator, i.e. the tombstone, isn't available, and so Cassandra will delete it, and then the replica goes, actually, hang on, there seems to be data missing now, I need to recover it, and the rows that you've deleted come back to life. For TTL data, don't combine TTL data with size tier compaction strategy. It just won't work. That's probably the most common problem we see. If you're using that, use time window compaction strategy. But if you use time window compaction strategy, don't mix TTLs. So have those different time ranges, use different tables. And the best way to avoid mixed TTLs is to actually set the TTL as a default on the table level rather than on every insert. So essentially, you can go like alter table, or if you're creating a new table, you can actually say the with default TTL is the number of seconds that you want it to be. If you're inserting nulls into tables, try and avoid this. And the way to do that is to use prepared statements and leave the columns unset rather than explicitly setting them to null. Because if you do set it to null, you will insert a tombstone, and that can actually cause that problem of when you do a read, a select, you will encounter a large number of tombstones, and you can actually start to hit those warning and error thresholds. And we've actually seen that for a number of customers where, essentially their application was setting, 20 out of the 30 columns in the table on every insert to null, and they were inserting thousands of records. And then when they do a, full partition query, they were getting back a couple of thousand records and hitting those tombstone warnings because they were actually inserting so many null values in the first place. So try and avoid that if you can. So an example is, don't do the first one, where you specify null for that particular column. Instead, use the setters on the prepared statements and say, set value for position 1, don't set position 2 at all, and then set positions 3 and any other values as well. So try and this requires some code changes, of course, if you are doing something like this, but you will end up not inserting nulls if you do the latter style of inserts rather than the former there. So some general solutions to tombstones, right, is, if you can get away with it, don't delete any data. And, as I said at the beginning, what good is a database if you can't delete any information? But, some strategies there might be, if you need to bulk delete information after a sort of unknown period of time, but you want a, the ability to do it. So you can't insert the records with a TTL at the beginning. Instead, maybe the right approach would be to create a separate table, say for a month, right? So you end up with a monthly table, which obviously complicates your queries, but at the end of the day, you could then drop an entire month table all at once, and dropping a table deletes everything instantly. You don't have to go through and explicitly delete all the records. and the end result is you don't end up with any tombstones, so everybody's happy. But if you do have to do data deletion, pick the right compaction strategy. Try and design your data model to avoid deleting large amounts of information if possible. If you're doing anything to do with time series information, use time window compaction strategy and explicit TTLs on inserts. And to avoid, if you do have a lot of tombstones, don't select an entire partition or something like that. Try and narrow your queries down, i.e. only query what's really necessary. So they're all kind of strategies to sort of mitigate the problems of tombstones. If you're running and your own clusters, monitoring tombstones is very important. For us, as part of our managed service for Cassandra, we actually monitor tombstones, and we even provide a graph of tombstones per read, which you can get either via our console or our API for this kind of information. But if you're running your own cluster, you can also get this information via JMX or from a Prometheus exporter as well. So on to the next topic, which is repairs, which is related to data deletion as well in a kind of tangential way, because it mentions, if you don't run repairs, you can have all kinds of problems if you delete data. But essentially, repairs are part of Cassandra's anti-entropy mechanisms, i.e., trying to reduce the amount of, sort of chaos in the system. And that's all to do, with kind of keeping consistency of information across all the replicas. There's actually various different types of repair mechanisms that run inside Cassandra. There's 3 of them. So there's hinted handoff and read repair. And both of those are automatic. They happen in the background, and you don't really have to do anything. Hinted handoff is essentially if a node is offline for a small period of time, another node in the cluster will actually become responsible for storing any writes that were supposed to go to that node as a hint. And then when the replica that was offline comes back online, the other node will replay those hints to essentially bring the other node back into sync with the rest of the cluster, and that's called hinted handoff. The other one is read repair, which is if you execute a query that involves multiple replicas. Cassandra essentially computes the checksums of all the data as you're reading it, and if it notices that any of the checksums are incorrect, it will go off and actually issue a repair in the background for the replicas that are out of sync. You're essentially, as you're reading data, you're kind of repairing any inconsistencies as well. Hinted handoff and read repair are both kind of tunable. There's various settings. Read repair is all done at the table level, so you can sort of set the chance that read repair will occur and things like that, though the defaults are usually pretty good unless you're seeing problems there. The last one on this list, though, is anti-entropy repair, or what most people, if you talk about repair in Cassandra, are usually referring to, which is a manual, or sort of, if you've got a tool, it's a semi-automatic process, but it's something that you have to set up and run and configure yourself. And it's basically the process of asking a Cassandra node to checksum all of its data and go and compare that with the other replicas in the cluster. And if any inconsistencies are found, to kind of synchronize all the stuff that's going on. The problems with doing that is that it can actually be very, very stressful because, if you've got a lot of data on a node, you basically have to read it all in and checksum it and then send it to other nodes. They have to checksum their data and do a comparison. And if there is any inconsistencies detected, you've got to stream data back to the nodes that are out of sync. So, there's a lot of disk IO work going on. There's a lot of network IO going on as well. So it can be, fairly stressful on a cluster. And it can become even more problematic if you're doing a multi-DC topology. So, you kind of got replicas stored in multiple separate geographic regions or something like that, that results in higher latency and various other things. So it can be even harder to get repairs to run without stressing the cluster. And the other thing is that they can be quite slow because they are fairly intensive. And so the issue there is that, they can be hard to run on a frequent scheduled basis. And if you are deleting data, the biggest problem is that I mentioned with Tombstones, you have that GC grace window of where Tombstones will hang around for that period of time before considering to be eligible for eviction off disk. You need to run repair within that GC grace seconds window. Otherwise, if there's any replicas that are out of sync, then data can come back. So if they're slow and they stress a cluster, it can actually be kind of hard to get it to run within that GC grace window. So, that's usually the main problems that we see is they're stressful, so people don't run them because their cluster's already at a kind of breaking point, or they're too slow to run successfully or on a frequent manner. And so the end result is that repairs don't get run in a timely manner or even on a scheduled basis. And part of the issue there is that because there is no out-of-the-box scheduling within Cassandra, you need something else to come along and execute the repair for you. We recommend a tool called Reaper if you are managing your own clusters. So it's essentially a tool that goes in and schedules and runs repairs for you and tries to minimize the impact that they have on the performance and the stability of the cluster. And the other thing a scheduler will do as well is kind of prevent you from trying to run multiple repairs on a cluster at the same time, because if you do that, multiple bad things can happen. Essentially, you've got multiple nodes all trying to compute the checksums all at once, which just adds additional I/O overhead, but then also trying to stream things between replicas while multiple repairs are running can actually cause those streaming sessions to fail. And so you've done all this work for kind of essentially nothing, because Cassandra will basically say, no, you can't run multiple concurrent repairs. So a scheduler is very, very useful to make sure that doesn't happen. So if you're running your own cluster, as I said, definitely check out Reaper if you're not using it. So when to repair, I strongly encourage anybody to run repair after you've had a node outage. Even if it's a small outage, it's probably the best idea to run repairs. But if you've had an outage that lasts longer than your hinted handoff window, which is configured in Cassandra.yaml, the config file, then it's almost necessary to run a repair, because you're basically saying that now Cassandra has decided that it's no longer going to store hints for the node that was down. So it's thrown all those away. And now when the node comes back online, it is most certainly going to stay out of sync with the other replicas in the cluster. So a repair is the only mechanism, alongside with read repair. But if you're not reading the whole data set, then read repair is not going to really help you here. Repair is really the only thing that can come along and detect that there's that inconsistency and fix it. So we sort of say you should actually run repairs on a frequent basis. So every n days, there's a little bit of a formula there. Essentially, it's using the value of GC grace seconds and giving you a little bit of extra headroom or whatever to determine what the interval in days is going to be. So use that formula to calculate how often you should be running repairs. If you don't repair, as I said, if a node is down for longer than the hinted handoff window, you can end up with inconsistent data. And if you don't run repairs outside of the GC grace seconds window and you have inconsistencies, you end up with data coming back from the dead. I actually have a little bit of a diagram here that's in a situation where you have 3 replicas and they all have a copy of a record. And what happens is one of those replicas, number 3, is offline when you issue a delete. So a client application goes along and says, delete the record. And what happens is that replicas 1 and 2, they receive a copy of that tombstone. But replica 3, because it's offline, does not get a copy of the tombstone. Now, replica 3 eventually does come back online, but it comes back online outside of the hinted handoff window, i.e. so replicas 1 and 2 are not going to tell replica 3 about the missed tombstone. They give up because replica 3 has been down for too long. And so what happens now is you end up in a situation where replica 1 and 2 have the tombstone and replica 3 has the original data. It has not been deleted. Now, if you were to do a read at this time, read repair would come along and fix the situation. But say you don't read the record, right? And you wait longer than the GC grace seconds window, right? So compaction comes along and goes, okay, on replicas 1 and 2, the original data and the tombstone are now eligible for cleanup, i.e. the data can be evicted off disk and the disk space reclaimed. So replicas 1 and 2 now end up with no trace of the record at all. But replica 3, because it's out of sync, still has a copy of the data. And now, if you were to run repair or do a read or something like that, i.e. invoke any one of these anti-entropy repair mechanisms, Cassandra will go, oh, well, hang on. There seems to be an inconsistency here. Replicas 1 and 2 are missing data, and replica 3 contains data. Maybe we should go and fix it because replica 1 and 2 seem to be out of sync. So what you end up with is the data reappears on replicas 1 and 2, and the data has come back from the dead. It's zombie information, right? And we've seen this happen in production clusters before. So definitely make sure you run repairs within the GC grace seconds window. It's very important if you're deleting information to avoid this kind of situation. So how to repair, I mentioned Reaper. So if you're running your own if you're managing your own cluster, definitely check out that tool. If you're using our managed service, we run repairs for you. It's daily by default, but we can customize that if necessary. But whatever you do, please don't run just node tool repair as part of a cron job on every node in the cluster, because you'll end up with running multiple repairs at the same time. There's no coordination, and you can end up essentially overloading your cluster or just not having repairs be successful because there's too many of them are running at the same time. So scheduling them is far, far better. So on to the next topic. So this is number 3 of the 7 things, is materialized views. And this is a fun one, and we see it happen quite a lot. They're an enticing feature, I guess, but please use them with extreme caution, right? They have a number of problems with them, and in fact, they have been retroactively marked as sort of a beta feature or experimental, right? On a Cassandra 3 cluster, if you actually go and create a materialized view through CQLSH, you will see a nice big warning that says they are experimental and they're not recommended for production use, but people use them for production use anyway. And as it turns out, actually, in Cassandra 4, they are disabled by default. You actually have to go in and enable materialized view capability for you to be able to even use these things, right? But there's a number of problems with them, and we've seen them take out production clusters. So think before you use them. The biggest issue, apart from them actually causing instability in the cluster, is actually the problem of you have no way, and Cassandra offers no ability to determine if the view or views and a base table are in sync with each other, right? How do you know that the data is actually in the view and in the base table? Whereas if you were to do the manual denormalization, i.e. have multiple tables and do inserts, and so if you've got 3 tables and you do 3 inserts, if the 3rd insert fails, you could always go back and retry it. Whereas in Cassandra, there can be situations where materialized views, you insert data into the base table, it says, yes, it's all successful, but the view doesn't get updated. And now the view and the table are out of sync with each other. And you don't detect it until you go and do a read. And the only way to fix it is to actually drop the view and recreate it, essentially get Cassandra to rescan the base table and recreate the view on top of it. Views also cause a bunch of problems to do with repairs and rebuilds. So, repairs are already a sort of stressful thing. Running materialized views on top of that can actually just make that worse. And they are also just, in terms of performance, have some issues where, when you do a insert, you kind of end up doing a read before a write and various other consistency checks, and so you end up with higher sorry, that's supposed to be higher write latency there, higher write latency on the views, and depending on, and I guess this comes down to data modeling in general, but if you create the materialized view with a poor choice of partition key, i.e. a value that has low cardinality, you can end up creating hotspots around the cluster. But that advice goes, it's true for if you create the tables manually anyway as well. So solutions to materialized views. Ideally, don't use them and do manual denormalization where possible, i.e. you go off and create your own set of view tables and do inserts into those tables when your application needs to add data to the database. If you need a little bit of kind of consistency across those tables, you can use logged batches, but logged batches do have a performance hit, right? So be aware of that. It might just be reasonable to keep track of whether or not inserts are failing or not, and retry those if necessary down the line. And that's where something like Kafka or something can come into play, where you have a queue of data to insert and you throw it back onto the queue if you need to retry down the line. Next is secondary indexes. So indexes make databases faster, right? And that's very true in the relational world. You look at the query plan and see that it's doing something a little bit weird, and usually if you create an index over the column that's a bit slow, suddenly the query runs a lot faster. That's not really the case with Cassandra. Use them with caution, because due to various scenarios, you can end up having a query hit every node in the cluster, which certainly does not scale. On a 3-node cluster, you're only hitting 3 things, whereas on a 50-node cluster, you're waiting for 50 responses to come back. And so the performance degrades as the cluster size increases, so not particularly good. So secondary indexes are a feature that, they're for a very sort of niche set of use cases, i.e. where data is infrequently updated, and the data has to have just the right cardinality to avoid the index getting spread across the entire cluster, and you having that problem of you end up querying every node in the cluster when you do a read. So we recommend doing manual denormalization of the tables, very similar to materialized views. And if you need additional flexibility, look at something like a proper indexing and search solution such as Elasticsearch, because it's going to be more powerful and more designed for probably the things that you're trying to do. And just to plug Instacluster again, we offer a managed service around Elasticsearch. We see people use this for indexing quite frequently because of this particular case where indexes in Cassandra aren't particularly performant and only really work for that very niche use case. So check it out if you need that capability. Next on the list is incorrect driver settings. And there's a whole bunch of things you can do wrong from the application side that causes problems with Cassandra. The biggest one that I see quite often, and this was actually a little bit surprising to me for a while until I dug into the driver source code and realized that this is actually the case, is where always use prepared statements, right? Just that should be, you know, never reach for execute that takes a string. Always prepare your statements. And the reason for that is prepared statements are the only type of query that you Cassandra that are token aware. And token aware means that the driver is able to send the query or route the query to the replica node that owns the data. If you don't do that, what you end up doing is sending the query to a random node in the cluster, you know, depending on the what do you call it, the load balancing strategy is, you know, probably going to be round robin or something like that. But you're essentially sending them to random nodes. And that node may not own any data for the partition that you're trying to read. And so what happens is that node essentially has to go, well, hang on, this isn't for me. It forwards it on to the node that does own that data. So it does the token aware routing. And now you've introduced a additional hop to access the information. So your latency goes up. So always use prepared statements because they're the only type of query in the Cassandra driver that is token aware. Like you can explicitly set the tokens on other statements, but you're essentially doing the work of the driver manually. So don't do that. Prepared statements are easy enough to use. Just use them, right? And just a little bit of kind of in-depth information into this is essentially the reason is that the drivers themselves, they do not parse the CQL statement text at all. Like they don't have anything to do with query preparation or processing of the CQL grammar itself. That's all on the server side. And if you prepare a statement, the driver sends the statement to Cassandra. Cassandra then returns back a whole bunch of metadata about that query. And included in that metadata is which kind of bound parameter positions in the query represent the partition key. And with that information, the driver is then able to say, okay, you have provided a value for the partition key. I am now able to hash that value and determine which node in the cluster is responsible or owns that that range of the hash space or owns that token. So in order for load balancing to work properly, you need the metadata, and only prepared statements provide that metadata. So just always use prepared statements. The other thing that comes up quite often is that your availability might not be kind of what you think you're going to be getting. You know, there's the kind of idea of, okay, if you have multiple nodes down in a cluster, you know, you're going to see a certain percentage of queries fail, which makes sense. But if your application is doing, and I use the term here loosely, transactions, right? Where a transaction is, you know, an application function that needs to, you know, query Cassandra multiple times, maybe for different partitions in the same table or different tables. And it needs the results of all those queries in order to be able to return a result to the caller, i.e. so it's the kind of, everything needs to succeed before we can return a result. And the problem with that is if you actually have multiple nodes down in the cluster across multiple racks, the chance of one of those queries failing, and as you add more queries to your transaction, the chance of the whole transaction failing actually goes up. It's a cumulative kind of increase in failure rate, right? So, you know, you might think, oh, well, we have 30 nodes in the cluster and only a small percentage of those nodes is down, so maybe only 10% of our queries should fail. But as soon as you introduce multiple queries, you're going to be doing different combinations of nodes to get the results of those queries, and your failure rate will actually go up because the chance of you hitting those nodes that are down goes up as you add more queries to the transaction, in quotes. So the solution to this is denormalize as much as possible. So you essentially only query from a single table. You know, I have a single query that returns everything that you need, rather than having to query table A, then table B, and table C. That also has the benefit of you know, it's going to be faster because you're not doing 3 reads, you're only doing 1. But it does increase the complexity when you do writes, because you are now having to, you know, denormalize the information and you know, store it in the various ways that your queries are going to have to extract the data back out. Which that is the kind of Cassandra practice, right? Is design your tables to match the queries that you're going to be executing. If you have to do things like client-side joins or multiple queries to get the data, you're kind of doing it wrong. But we do see this quite often, where people execute multiple queries to get the result, and therefore the availability is not what they're expecting. Also, we see quite often, you know, people that run multiple Cassandra data centers, so a multi-DC cluster. They do it for, you know, availability purposes, which, you know, is totally reasonable. And so, you know, you end up with a scenario like this, where you you have 2 regions. Each region has a Cassandra data center in it, and each region also has an application instance. And say Cassandra in DC1 goes offline, the kind of old approach to failover was have the application instance in region 1 start talking to the Cassandra database, or sorry, data center in region 2, as this diagram shows here, right? So the traffic gets rerouted across regions. The problem with this kind of setup is that usually the Cassandra DCs are sized to be capable of handling the load that the local application instance is putting on them, but probably not much more. And now, if DC1 is offline, application instance 1 is routing all of its traffic over to DC2, and now you have 2 application instances hitting one Cassandra DC that was originally only designed to handle the traffic from 1 application instance. So then end up having Cassandra DC under a lot of stress, sorry, DC number 2 under a lot of stress, and it may even catch on fire and eventually die as well, and then you have a full outage. So instead, and this has actually been kind of implemented as a pattern in the newer versions of the Cassandra drivers, where the load balancing policies will not allow you to do kind of cross DC connectivity. Instead, what they say is, if Cassandra in a particular region is offline, consider the application to be offline in that region as well. And then have a load balancer that sits between the client and the application instances actually recognize that fact and instead route the traffic over to the other app instance. And that load balancer should be intelligent enough to know how much traffic each application instance is able to handle. And it may be able to shed load or throttle requests, something like that, because it now knows that you only have half the capacity that you previously had because you have one region offline. So essentially, as I said, DC-aware round-robin policy, which was the thing that allowed you to do this kind of strategy where app instance 1 now talks to Cassandra DC2, it's been removed in the version 4 of the Cassandra drivers. And instead, they say, do it with the front-end load balancer. Shift the problem up the stack to something that sits in front of the applications. We also see people a lot using batches in Cassandra. Don't use batches unless your use case fits exactly within the niche use case that Cassandra batches are actually designed for. You know, people kind of go, oh, well, you know, I use batch statements in my, you know, relational database to make things faster. And, well, it doesn't really do that in Cassandra. There's 2 types of batches. There's logged and unlogged. Logged batches are designed for doing kind of atomic inserts in quotes, right? They allow you to do consistent denormalization, i.e. you insert into multiple tables and those inserts, they all succeed or they don't. But be mindful that they're not like a transaction in a relational database. There is no isolation of reads. So meaning that if you are in the middle of running a batch and it's updating 5 tables and you do a read, you may see 2 out of the 5 tables actually containing the data. So there's no read isolation going on. It's purely a ability to easily roll back the inserts if one of them fails, right? So it's good for doing that denormalization, which is, you know, when you're trying to implement your own materialized views or your own indexes. The second, which is unlogged, it's just a group of statements. And that sounds great for doing bulk inserts, right? Because it's going to be faster and whatever. No, well, the problem again is that there is no load balancing on batches. And so what happens is you end up just throwing it over the wall and letting Cassandra deal with it. And it is then required to essentially split the batch up and divvy up the individual pieces to the various replica nodes that are actually responsible for the data. So instead, just send individual insert statements to Cassandra, let the driver route the queries itself, use prepared statements, and you know, you will get better performance because Cassandra is no longer having to involve a coordinator and various other things. And you know, if you want additional performance, you can use asynchronous queries, so they all happen at the same time. You know, there's a bunch of different ways to do it. Just don't use batches; they're not faster. Lastly, and this is probably we're starting to see it in, like, you know, the Kubernetes world and things like that, is sticking a load balancer in front of Cassandra. You know, something that maybe operates at the TCP level or something like that. This is a bad idea, right? The driver, i.e. your application, wants to connect to every node in the cluster, because that's how you do token-aware routing of queries, i.e. sending the query to the most appropriate replica in the cluster. If you have a load balancer in front of you, then you're unable to do that. The driver cannot route the queries appropriately. And a load balancer introduces a single point of failure, which completely defeats one of the points of Cassandra, and why people use Cassandra is that it is a you know, shared nothing architecture. You can send the query to any of the replicas and you'll get a result back. If you introduce a load balancer, if the load balancer is offline, you can't access your database. It's, you know, it's pointless. So not a good idea. Next is poor schema design and denormalization. So I kind of touched on this a little bit already, which is, you know, when you do client-side joins and things like that, there is, as I mentioned before, you know, the potential for that to have problems with availability because you're doing multiple queries. But also remember that these are going to be synchronous, because you have to query table A, then table B, then table C. So you have to wait for the results from each of those queries to happen. And it also adds additional stress on the whole cluster because you're doing multiple read queries. So ideally, you don't do client-side joins, and instead denormalize your data set further and aim for a single query to you know, fetch everything that you need. So you can send one, bam, you get everything back. That can be a little bit challenging, and you could end up with a lot of tables. But you know, the end result is Cassandra's design is writes are cheap and reads are a little bit more expensive. So optimize for writes. Write as much as you need to so that you don't have to read as much. So it's all about denormalization. Another one is large partitions, specifically partitions that are unbounded. This can cause hotspots around the cluster, i.e. certain nodes are under more stress than others. And Cassandra internally, various things happen on a, you know, whole partition basis. This is less of a thing with newer versions, but it can still happen. But the issue there is large partitions can cause, you know, various memory pressure problems, which kind of, you know, involves the garbage collector more frequently. That results in, you know, pauses, higher latency latency, bad things happen, etc., right? So really keep your partition sizes below 100 megabytes, kind of like the safe watermark that we usually recommend. And if you are going to end up with an unbounded partition, use a clustering column to bound them, right? So a common thing there is maybe time series information, where you essentially have a partition key and then a timestamp as a clustering key. And the problem there is, if that partition is going to be around for a long time, you could end up with, hundreds of thousands of records inside of a single partition. Instead, what we'd recommend is split the timestamp into buckets, or into chunks or something like that. So the example that I give here is maybe you could involve a new partition every day, right? So you end up with partitions are only going to contain a day's worth of data at a time. So the result there is that you always know that the size of a partition is going to be it'll never go over a particular limit. And you then don't end up with the problems of large partitions as a result. Obviously, it does make it harder to query the information, because if you need to query data across multiple days, you now have to run multiple queries. So it's a bit of a trade-off, right? But large partitions are a problem. So design your data model to approach this. Also related to partition keys is partition keys with low cardinality. So don't use something like a Boolean value as a partition key, or a enumeration that has maybe because the result is that you end up with a data imbalance across the cluster. If you have 50 nodes and 2 partition keys, you are not going to be able to use all 50 nodes to service your queries. Essentially, it's going to be 2+ replicas at max if you've got a Boolean value as a partition key. So try and increase the cardinality of your keys where possible. And one solution to that is shifting various attributes from just regular columns into the partition key. That, of course, can sometimes be a little bit challenging to try and find a good candidate there, because the issue with the partition key is you need to know the value in order to be able to query the row. So things that are random identifiers or something like that, unless you have another way of determining those values, it can be a difficult thing to move into the partition key. But yeah, make sure that you don't end up with low cardinality partitions, because it can cause hotspots. Also, don't use large collections and blobs. So that kind of goes back to the large partition thing. So, if you've got a large collection or a large blob inside a row, it can make partitions kind of big. The thing with blobs as well is that there's, and collections, sorry, is that there's no way to paginate through these things. So if you have a blob that is 50 megabytes the size, you copy the whole 50 meg into the client memory buffer all at once. You can't read it piecemeal from the cluster. So don't store images and files and things like that in Cassandra. Store those somewhere else, on the file system in S3, something like that, and include a reference in your table instead. Then lastly, unoptimized queries. So we're getting towards the end here. Is have a look to see if your application is doing any multi-partition reads, i.e. using the in clause in those in the CQL text. Essentially, this is a thing where it's kind of like a batch, right, for a select statement, where you end up sending the inquiry to a coordinator node, and then the coordinator literally just has to split the query up into the individual components and send those to the appropriate replicas. And this might sound familiar. That is not really the right way to do it. You should be getting the driver to send the queries to the right replicas, not involve a coordinator, and do the load balancing as appropriate. So the solution there is to just not use inquiries and execute the individual partition queries explicitly, and you could run those asynchronously if you wanted to, right? So you could you know, have them all be running against the cluster at the same time, and use prepared statements. I can't say make that statement enough. Is use prepared statements on everything. Another thing we see often is allow filtering. So that is where Cassandra's query language, CQL, is fairly limited in the types of where clauses that you can put on a query, you know, so the types of statements and comparisons and things you can do. Allow filtering kind of removes that restriction. But the problem with that is that Cassandra is unable to really do an allow filtering query without doing a full table scan, which can be very expensive, and on a large cluster is certainly not scalable. You know, so they're good for doing, you know, debugging or something like that on a developer cluster, but definitely not something that you should be doing against production workloads. You know, if you see allow filtering in your application code anywhere, definitely have a closer look at exactly what's going on, because it's probably not what you want to do. So I'm just having a look at the chat here. We've got a couple of questions coming in. So I'll go through those in a minute. We have a Q&A section at the end of the presentation here. So just some closing remarks. So we have a bunch of open source projects related to Cassandra that I encourage everybody to go and check out. If you're running your own cluster and you need monitoring and metrics available, check out our Cassandra exporter. It integrates with Prometheus, the monitoring solution. The exporter that we've written is extremely fast. It bypasses JMX, able to collect, you know, all the metrics of your Cassandra cluster all the way down to the table level in far less time than existing solutions, you know, collect all the data, and it's you know, therefore it's going to put less stress on your cluster as a whole to do monitoring and metrics collection. If you're in a enterprise environment and you're running, you know, Active Directory or Kerberos and LDAP, check out our Kerberos LDAP plugins, which provide integration with those technologies and allow you to do authorization and authentication against Kerberos and LDAP. We've provided a bunch of fairly low-level diagnostic tools as well. So that's Insta-Repair and the Cassandra SS table tools. Those are more, you know, if you get stuck in sticky situations to do with repairs or need to see what's going on inside an SS table at an internal level, you know, those tools can help you out there. And then we also have a backup and restore utility that, you know, does what it says on the tin, lets you, you know, back up and restore Cassandra's SS tables and commit logs and various other things to cloud blob storage infrastructure. And it's actually very similar to the thing we use internally as part of the managed service. So, you know, it's been well battle tested as well. Instacluster, we're 100% focused on open source. So all the technologies that we run, Cassandra, Kafka, Spark, Elasticsearch, and Redis, we use and run the open source versions of those technologies. So for Cassandra, that is the Apache Cassandra distribution. Reach out to us if you would like to see a, you know, proof of concept or have us run a demo or something like that. And also definitely reach out to us if you need any assistance with data modeling or application development or something like that related to these technologies. We have consulting services available to assist with that. And we can also run developer workshops and operations training and things like that. And so, you know, an example of a workshop on a developer side is various things that we discussed today, but at a lot lower level. So we go into each of those topics at an hour at a time, if not longer. Look at the internals of Cassandra's data model, various other things. So it's fairly in depth. If you'd like to discuss consulting and workshops and things, reach out to Anil. His email address is there on the screen. Anil is our managing director for consulting here in America. So he's certainly the right person to talk to if you need help with that kind of stuff. All right, on to some of the questions. I saw that they popped up in the chat window. If people do have additional questions after this, reach out to me or support@instacosta.com. We're happy to answer those as well. But let me just go through the chat here and see what we have. Are the slides or the presentation going to be shared? Yes, I believe so. And Bill, maybe you're able to answer that a little bit better. I believe the whole thing is being recorded, so it's going to be shared up on YouTube. Yes, but we should be able to provide a link to a PDF copy of the slides as well somewhere. Yep. Another question is, does Cassandra work better than SQL for storing data? Okay, that's a fairly generic question, I guess, and it's sort of hard to answer without really knowing the use case a little bit better. Cassandra is really good at storing high volumes of information that come in on a very, very frequent basis. So, think of, IoT sensor readings or, information from, internet advertising clicks or, gaming score statistics or all that kind of stuff. Lots and lots of small pieces of information coming in at a very, very high frequency, and that where you're storing and collecting that, and the amount of data that then is going to be read back is going to be less. You might only be receiving the latest piece of information or something like that. Cassandra is more limited in the types of queries that you can run, and I touched on that briefly with that allow filtering thing, where SQL, you can kind of do all cool kinds of things. You can join tables together and kind of manipulate and kind of convert the data into the various forms that you need as part of the query. Cassandra, the model really is, you create tables based on the types of read queries that you want to be able to run, and then you insert the data to that model, right? And so if you've got 10 different types of read queries that you need to run, you end up with 10 tables, and you have to do 10 inserts every time you get more data coming in. So essentially it's different, and whether one is better than the other really then comes down to the individual use cases. I think do we have time for maybe one or more?
Yes,
questions,
yes. I think we have quite a few questions. Yeah, we have time to go over all of them.
Okay, cool. So how do we guarantee or force delete specific records? So to force delete a specific record in Cassandra, you issue a delete statement as you would in any other database, and that will actually delete the record. If you then do a select, it will not be returned to the client, but it does write a tombstone to disk. And so that was the whole thing I was talking about, where if you force delete a large number of records, you end up with a large number of tombstones, which can degrade performance over time and start to cause problems. So try and avoid that if possible, by either using TTL'd data, if you know upfront how long you want to keep stuff around for, or potentially creating, tables that are, fairly coarse-grained in terms of the sort of information that they represent. So maybe it's a monthly table or even a yearly table or something like that. But you can then say, well, we don't need that information anymore. Let's just delete the entire table, just drop the entire table, and it's going to be a lot faster. when would you recommend a cloud SaaS offering like DynamoDB versus Cassandra? Well, if you need Cassandra as a SaaS offering, that's what Instacluster does, right? So that then really comes down to a DynamoDB versus Cassandra kind of discussion. And they are similar, but they have various different types of limitations and the things you can do. I'm going to be slightly biased and say I think Cassandra is better than DynamoDB. That's just me. And there's some benefits there, not only on a tech perspective, but also DynamoDB it's an Amazon specific technology. You can't run it on another cloud provider if you want to, whereas Cassandra you can run it on-prem or any cloud provider if you want. So it's more about that kind of vendor lock-in kind of aspect, right? But DynamoDB does have some benefits over Cassandra in certain cases. It has some better integrations with various other Amazon or AWS technologies that they provide. So when data is deleted, my understanding is you can have it trigger something to happen. In Cassandra, that's a little bit harder to do out of the box. So there's just a little bit of a trade-off, right? But yeah, as I said, if you're looking for a managed solution, so a SaaS solution for something like Cassandra, that's what we do at Instacluster. So it's not really a Dynamo versus Cassandra, because Dynamo is cloud and Cassandra's local data center. It's more of a which technology is better for your use case. And then another question here is, how are the recent versions of Cassandra for storing consistency use cases like a relational database management system? Can we ever use it for ACID? So no, and okay, that's just a very broad no. There's certainly things that you can do to improve various cases, but Cassandra does not offer transactions. It does not offer read isolation. So all that kind of stuff. So essentially, if you're trying to do that kind of stuff, Cassandra is not the best use case. And I think people get a little bit confused about, when they hear Cassandra is all about, eventual consistency and tunable consistency and all that sort of stuff. It's all about trade-offs where, Cassandra's consistency and availability is tunable. At one end, you can actually say, I want an acknowledgement from every replica in the cluster, which is going to guarantee you strong consistency, but your availability guarantees are right out the window. On the other end of the spectrum, you can actually say, I only care about receiving an acknowledgement from one replica in the cluster out of, say, 3. But so that guarantees you very, very strong availability. You could have 2 out of the 3 replicas offline, and you're still able to run and execute that query. But the end result is that your consistency guarantees have gone out the window. There is actually a good middle ground, which is, the kind of golden configuration that we often recommend to people, which is essentially if you have a replication factor of 3 and you read and write at quorum, so that is 2 out of the 3 replicas, the reads and the writes overlap in terms of the replicas that they're interacting with, and therefore you guarantee consistency and a reasonable level of availability. Like you can have a single replica offline and the data is going to be still available and the data is going to be still consistent. If you have 2 replicas offline, well, then that's a problem. You can no longer achieve a quorum, so your queries will start to fail. But it comes down to, it's an application design decision. What level of consistency and what level of availability do you want? You can even go so far as doing strong consistency on your writes to guarantee the consistency of the data, so that you can then do a single replica read out the other end, or the opposite. You write with consistency level 1 and read with consistency level all, and you can then get strong consistency as well. So it's all tunable. It's all customizable. And then lastly, I think this is probably going to be the last question. Oh, okay. Got a bunch coming in here, but okay, maybe this talk about why table level TTLs are better than insert level TTLs. That's a very good question. So I think it really comes down just to preventing mistakes. So if you use a table level TTL, you're guaranteed that every record that's inserted into the table has a TTL and that they're all going to be the same. Whereas if you're doing insert level TTLs, you can end up in a situation where maybe you've got multiple client applications writing into that table, and some of those applications are setting TTL values and others aren't. So now you have a mix of non-TTL data and TTL data, which is problematic. Or the different applications might even just be doing different TTL values. And that is also a problem because you're now mixing TTLs, and time window compaction strategy is going to be less efficient at reclaiming space off disk. So I hope that answers your question.
Okay, I think we still have a few questions. We are over 20 minutes over times, but I want to make sure we actually have a couple of questions from Slack. I just want to give them a chance to answer the questions if you have maybe a few more minutes.
Yeah, I'm happy to hang around and answer these.
Okay, that's great. Yeah. So I can just quickly read it. So the first one is more kind of like a comments. So you mentioned about the compare the Cassandra and the DynamoDB. Is it fairly to say Cassandra is kind of like an improved version of DynamoDB or Bigtable?
So, okay, historically, Cassandra and DynamoDB, and this is to the best of my knowledge. I mean, DynamoDB is a proprietary solution from Amazon, right? It's just sort of what you hear through, various presentations and grapevines and things. But, Cassandra and DynamoDB share a kind of common origin in a way, Bigtable and the Dynamo architecture. But in terms of, is one better than the other? I think they're really just, they solve different sets of problems, and it's, Dynamo is perhaps a little bit more elastic in terms of its scalability, but, there's also a cost element to it. As I said, it is a proprietary solution. It only runs on one provider. Cassandra is a little bit more flexible. You can do all kinds of, fun things with it. So, it comes down to, I wouldn't say that Cassandra is like an improved version of DynamoDB. It's more of a, it's another tool in a sort of same space. In the broader NoSQL database ecosystem, there's kind of these, key value stores, of which, Cassandra, and all the kind of like distributed hash table kind of storage engines and things. Cassandra's in that, DynamoDB's kind of in that space as well. And so, it's then picking the technology that best suits your use case based on, the various aspects, rather than is one better than the other.
I see. Another one is, can you say a bit about raw logs? What will happen if there is a lot of updates and reads of the same row at the same time? Is there kind of like a deadlock?
So the question is, does Cassandra have any concept of row locking, and what happens in that case? The answer is no, it doesn't. The last write always wins, right? So essentially, you do an insert, and that insert will be written to multiple replicas. And if you've got multiple applications all doing inserts at the same time for the same row, the record with the latest timestamp will win. It's as simple as that.
Okay. Okay. So
sorry. Just to add to that, like there are the concept of doing lightweight transactions in Cassandra. So that is where, if a record does not exist, or if a particular value is equal to this thing, but they are a lot more expensive in terms of, the amount of work that Cassandra has to do. It essentially has to do, multiple rounds of coordination between the various replica nodes in order to do lightweight transactions. So your insert performance will go way down, right? So don't use them unless you really, really need to use them.
Okay, so we have 2 questions in the Q&A. Maybe you can just pick one for the last questions.
Yeah, I can. So the one here about which version of the driver that removed the auto failure capability, that is version 4 of the, I'll click the answer live button actually. So that is version 4 of the Cassandra Java driver removed that failover capability. And they now recommend that you push that up to a kind of application level load balancer or something like that.
Awesome. I think that's our last questions, and we are 30 minutes over the times. Thanks a lot, Adam, for the great presentation, a lot of information, and stay over time to answer the questions with us.
It's been a pleasure. Thank you for having me. And yeah, if anybody has any other questions, you can reach me at my email address, adam@instacluster.com. Thank you very much, and have a pleasant day. Bye.
Okay, great. Thanks. Thanks again. Thanks everyone for joining us today. The session recorded. We will share the recordings and also the slides shortly in the follow-up emails. I hope to see you all next events.